Okay, if not, I will give you after at around 9, I will give you a quick break, maybe about 10 minutes, 15 minutes, and then I will ask about 30 minutes of your time because there's no way we can finish the rest of module number 3 and all of module number 4 in just a 2 week in a 2 hours course. And on the other hand, next week is the schedule for the first module exam. Okay. All right, one of you have a class. Okay. So yeah, I think we need to have an extra 1 hour schedule sometime this week. Okay. So
Mickey, maybe this lecture is recorded, so if Gamma have a class after this, he can check the
oh yeah,
record. Yeah.
yeah. Okay, so there's only if there's only one of you who have class, then yeah, so we can continue about until about 9:30, and then for those of you who are not able to attend after 9, you can certainly watch this recorded session. Okay. All right. So let's first continue our discussion on sampling distribution. Now, the version that you're seeing now is a bit different from the one that has already been uploaded. So I've edited some terms. Um, I will make sure that the edited version will be uploaded later on, right after class. Okay. So, okay, let me hang on a second. There we go. Now, this is an important concept. There's no math that's going into this current submodule or segment, but it contains a very important concept that we have to go through before we discuss inferential statistics. Okay, so to give you an idea what what sampling distribution is, I will give you one example of. So suppose we are asked to do a study on how much electricity is being consumed by the average household in Bandung. Okay, so this is a problem. We want to do a survey of household electricity consumption per family in Bandung, but on the other hand, we don't have enough time and resources to carry out a census. So there's no way for us to perform to measure the average annual electricity consumption of all households in Bandung. So we have to do sampling, which somehow must represent the entire greater Bandung area. Okay, so the population here is defined as all family members of Bandung City residents. Okay, so that is how we define our population in this case. Surveys are carried out through sampling because in this case we don't have enough resources to do census, in which one sample is defined as 10 families per subdistrict. So subdistrict is kelurahan. Okay, so in this case, again, the sample size is n equals 10. No, there's a bit of an important concept here, or term rather, not concept. So you have to be able to differentiate between sample size and sample number. Okay, so in this case, because there are 151 kelurahans in Bandung, so the number of samples, jumlah sampel, is 151. And because from each kelurahan, we're taking a sample of 10 houses, okay, 10 households. So the sample size is 10. Okay, so please again distinguish between sample size and sample number of samples. Okay, so again, in this case, the number of samples is 151, which is in accordance to the number of kelurahan in Bandung, and the sample size. So how many household is being observed per kelurahan is 10. So we say n is equal to 10. So n always refers to sample size, not number of samples. Okay, so please do not confuse between these two terms. Okay, so we have number of samples, we have sample size. In this case, sample size is 10, number of samples is 151. And what we do with the 151 samples, okay, so when we say samples, we do not refer to the 10 households. We refer to the 151 kelurahan. Okay, so what we do in each kelurahan, we take the data from 10 households. okay, and we calculate their average annual electricity consumption. Okay, so the raw data will be 10 households times 151 kelurahan. So we will end up with 1,510 individual data. Okay, and the individual data are, again, annual electricity consumption, okay, from each household, right? So what we're seeing here, these are sample means, rata-rata sampel atau rata-rata cuplikan. Okay, so what we do again for each kelurahan is we take the average. Okay, we take the average electricity consumption for each kelurahan. Okay, so each kelurahan will generate one number, one average number, which is calculated from 10 households. Okay, and these are the numbers. So for example, X bar 1, this would be the mean of sample number 1. Okay, so sample number 1 is taken from some kelurahan and kecamatan somewhere. Okay, X bar 2, this is sample means for sample number 2. X bar 3, X bar 4, and so on until all the way to X bar 151. So this is the means of sample number 151. Okay. All right. So, and these are the samples. Okay. So again, these are the districts sorted according to alphabetical order. So we have Kecamatan Andir, for example, Kecamatan Andir consists of 6 samples. Okay, because this kecamatan holds 6 kelurahan. So each kelurahan becomes one sample. Okay, one sample consists of 10 households. Yeah. So we will end up with 151 numbers. We will end up with 151 sample averages or sample means. Now, remember what we discussed in the first week of class, or second week, I think. Any data, any measurement data, can be represented as a frequency distribution, right? So if I were to give you, if I give you these numbers on the right-hand side here, and I'm asking you to describe the data as you have learned from last week, from week number 2, how to describe data using using graphics and also using data descriptors. Then what you can do with these numbers is to plot them as a frequency histogram, right? Jadi data apapun, data pengukuran apapun, kalau saya berikan ke kalian angka-angka ini ya, ini adalah notabene lagi-lagi ini adalah angka rata-rata cuplikan. Karena kita punya 151 kelurahan, maka kita punya 151 buah nilai rata-rata cuplikan. Ya kan? Dan angka-angka apapun itu bisa diplot dalam bentuk histogram frekuensi. Ini bisa kalian cirikan dengan besaran-besaran penciri data. Average, standard deviation, variance, and so on. Okay. You can also calculate, if you want, you can calculate their kurtosis, their skewness, and so on. Okay. So what we get, if we express these numbers in terms of frequency distribution, so that frequency distribution is called sampling distribution. Okay, so sampling distribution consists of sample descriptors. In this case, in this one particular case, what we do, because we plot the frequency distribution of sample means, that what we get is sampling distribution of the means. Ya, jadi kalau kita katakan distribusi cuplikan saja nggak cukup, kita harus lengkapi. Ini apa yang kita gambarkan ini apa? Dalam kasus kita ini, karena yang digambarkan adalah rata-rata cuplikan, maka distribusi cuplikannya adalah distribusi cuplikan rata-rata. Okay, you can do the same procedure for any other sample descriptors. For example, you can do similar procedure using sample variance. So instead of means, what you calculate here are the sample variances from each kelurahan. Then if you plot the frequency distribution of the sample variances, then what you obtain is sampling distribution of variance. Okay. So here's how that data looks. Roughly, it will look something like this. Okay. So again, yeah, if you any frequency distribution can be characterized by data descriptors. Yeah. Now, this is one of the most, sorry, this should be a theorem. There's an M missing there. Okay, so central limit theorem. So for any form of population distribution, so it doesn't matter the shape of the sample distribution. Okay, for the sorry, population distribution. Okay, doesn't matter what the shape of the population distribution is. If we take um, sample means from the population and we construct the frequency distribution of the sample means, then the distribution will approach normal shape, will approach normal distributions. Okay. This is what's actually what is being depicted in the previous slide. Okay. So this one here. Okay. So it doesn't matter what the shape of the frequency distribution of the original population. If we collect sampling distribution, the sampling distribution will approach normal shape, normal distribution. Okay, remember what normal distribution looks like. Okay, okay, and this sampling distribution, it turns out the mean of the sampling distribution of the means will approach mu. Now remember, mu is the population mean. Okay, which in most cases cannot be measured exactly. Yeah. Okay. And the standard deviation of the sampling distribution of the means. This gets a little bit confusing. But you can again you can always replay this video. Okay, so the standard deviation of the sampling distribution of the means will approach sigma divided by square root of n. And you know that sigma is the standard deviation of the population, not the sample, but the population. And n, okay, n is the sample size. Okay, larger sample size will give us closer approximation to normal distribution. Okay, so what these mathematics mean? Okay, it means there's a clear relationship, okay, clear mathematical relationships between population parameters and sample statistics. Now remember from our course on descriptive statistics, okay, so population parameters are besaran-besaran penciri populasi. Okay, population descriptors, population mean, population standard deviation, and so on. Okay, whereas sample statistics are descriptors of samples. Okay, there you go. That one. Okay, so we have a correlation, a clear correlation between these two quantities. So this implies that we can represent population by using sample. Now, this is probably something that you think might be already intuitive, but actually it has a very, very profound impact on statistics. This justifies our entire curriculum on statistics, meaning that mathematically, we can prove that a population can be represented by a sample taken from it in a proper manner, of course. Okay, now let me give you an example. Okay, just a simple graphical example. Okay, now let's say that you're this millennial farmer. Okay, so you want to fertilize, you want to perform a fertilization of your soybean farm. Okay, ladang kedelai. Yeah, so you have to make sure that this large plot of soybean farm gets proper dose of fertilizer. Yeah. Now, of course, there's no way that you can perform a census of all of this land. Ya, jadi tentu saja kita nggak mungkin melakukan pengukuran untuk semua lahan ini. Tidak praktis, impossible, ya, tidak mungkin. Apalagi sampling dari soil tersebut, dari tanah tersebut dicari dengan alat seperti ini ya. So of course, the quantity of the soil that you obtain from each sampling will be very, very tiny compared to the entire land, right? But you have to make decision about how much to fertilize for the entire land, for the entire farm, based on very, very, very limited samples. Okay, so somehow you have to be able to draw conclusions about your entire population based on a very limited sampling data. And that is what statistical inference is about. And again, the justification of that is sampling distribution and central limit theorem. Okay. All right. Now, this is a good quote. We don't have time to go through it in detail now, but this is actually contained in a statistics textbook that I used when I was your age. Okay, and read about it. I think it's a very good motivation to really understand our world based on statistics. Okay. All right. Any questions here before we move on to the next chapter? Okay. If not, I'm gonna need a 5-minute breaks, and we will continue to module number 4. Okay. So just a 5 minutes break. Okay, now I'm going to show you what materials we have uploaded in EduNext. So where is that Nginx? Oh, here we go. Okay. So this is the menu that we have uploaded in Nginx for module number 4. Sorry, that one. This one is module number 4. Okay. So we have three. We call them. We call these material segments. Okay. Segments 4.1, 4.2, and 4.3. And each segment has already equipped with videos. Okay. Yeah. So the first one is concept of inference. So we will discuss about the basic principles of statistical inference. Okay. And the second one, oops, what's going on here? Okay, here. This gets a little bit crowded. There you go. And the second one, so this is the first part of what is called a statistical inference. Again, statistical inference are a set of mathematical procedures that enables us to draw conclusions about population parameters, okay, based on sample statistics. Okay, so parameters and statistics are they refer to besaran-besaran penciri. Okay, when the context is besaran penciri populasi, then we say population parameters, parameter populasi. When we talk about samples, then the term becomes sample statistics, statistik sampel. Jadi parameter populasi dan statistik sampel itu analogi satu sama lain. Ya. So, for example, I say rata-rata, means or average. So when this number is assigned to a population, then we say population average or population mean. So that is one example of population parameter. When that rata-rata is calculated for a single sample, so that's called a sample mean or sample average, and that is one example of sample statistics. Ya, parameter populasi, statistik sampel. Jadi statistik sampel adalah besaran penciri sampel. Ya, rata-rata sampel, simpangan baku sampel, varian sampel dan seterusnya. Ya. Oke, jadi inferensi statistik adalah prosedur yang digunakan untuk menarik kesimpulan tentang populasi berdasarkan data sampel. Oke. Okay, so in segment 4.2, we will discuss about how to calculate what is called confidence intervals. Yeah, for means, for population means. Then in the last segment, we will discuss how to calculate confidence interval for population variance. Ya, jadi kita akan belajar bagaimana cara menghitung selang keyakinan. Ya, selang keyakinan untuk rata-rata populasi dan selang keyakinan untuk varians populasi. Now, I'm gonna let you guys watch the video. Actually, in total, the video runtime is about 20 minutes. Okay, I'm not going to ask you to watch the whole three at one time, but for now, I would like you guys to watch the 4.1 video. Okay, concepts of inference. I will give you guys 10 minutes. It's a little bit of a short one. Okay, so well, actually, I'm gonna give you. Yeah, it's okay. 10 minutes. Okay, so we will reconvene at 8 a.m. Okay, and then for 4.2 and 4.3, I will flip the way we study. So I'm not going to ask you guys to watch the videos, but I will explain it using the PowerPoint because we have to discuss a lot of things. We also have need to discuss how to use standard statistical tables that is available in textbooks. Okay, so just watch 4.1 and then go back here. Okay, so we'll meet again at we will meet again at 7:40. Okay, 7:40 a.m. Okay, go ahead. Okay, welcome back. So just to recap of what you guys have just watched, okay? I think this one is pretty obvious, okay? So this one gives you an example of what um, statistical inference is about. Again, so again, we need to somehow draw a conclusion about the population based on a very limited sample, okay? And actually, if you think about it, situations like that actually is abound in chemical engineering because most of the systems that we study is associated with conceptual population, and there's no way that we can do a census for a conceptual population. Okay. Okay, so there are two main activities in statistical inference. First one is parameter estimations, meaning these are the procedures that is associated with how to find the best estimate for population parameters. Okay, again, and the reason for this is because we cannot know for certain, we cannot know for exact the value of the population parameter. So therefore, we are limited to only finding its estimator. Okay. The second activity is hypothesis testing, which is the procedures by which we test the acceptance of a claim against a population parameter. Okay, so this will be simply like, okay, so let's say that I make a claim about the average GPA of ITP students, ITP undergraduate students. Okay, so let's say maybe I made a statement like, okay, so the GPA of all ITP undergraduate students is not more than 3.5. Okay, so that's my claim. So I'm making a claim against a population parameter, which is in this case is the average GPA of the entire undergrad students with ITB. So that claim needs to be checked. Okay, and the procedure for checking that claim is called hypothesis test, right? I think this one is pretty already pretty clear. Okay, point estimate is these are individual numbers which describes the population parameters. Okay, so the name might sound a little bit intimidating, but actually, when you say, let's say that I give you a basket of these onde-ondes, okay, and I ask you to measure their average weight, average mass, okay, and then you come back to me and report, Pak Walmiki, so the average weight of these onde-onde is perhaps like, maybe 50 grams per piece, okay. So when you give me just one number, it means that you're providing me with a point estimate, okay. Let's say that, okay, look, so going back to our onde-onde examples, let's say that I give you a large number of onde-onde, and I give you only a limited amount of time to tell me the average mass of one piece of onde-onde. Okay, let's say that I give you 1,000 onde-ondes. Okay, so because there's no way for you to measure each and every piece of onde-onde, then you take a small number as sample from the population, and then you measure the mass of the samples, okay, and then you report back to me, Pak Walmiki, so based on our sampling, okay, which consists of n number of onde-ondes, the mean mass of one onde-onde is 50 gram. So when you quote that number, it means that you're giving me a point estimate, which is just giving me one number. You're not telling me yet about the uncertainty, the lower limit or the upper limit of your estimate. You're just giving me one number. So that's, again, that means that you're giving me a point estimate. Okay. Now, of course, another way and better way to express parameter is using interval estimate, interval selang. Okay. So being an interval, it has lower and upper bounds. Ya, karena namanya selang, maka dia ada batasnya. Ada batas bawah dan batas atasnya. Oke. So when you do this, you report to me, okay, Pak Walmiki, so the average mass of one piece of onde-onde is 50 gram plus minus something, okay, plus minus sampling error. Okay, so that means you're giving me an interval estimate, not point estimate. Okay, right. So there's that. I think that covers the introduction to statistical inference. Now let's talk about specific methods to calculate um, confidence intervals. Okay. 442. Okay, there you go. Yep. Okay, so the first statistical inverse method that we discuss is called confidence interval of the means. Okay. So the true value of population parameters usually cannot be exactly known. Okay, because again, if you're dealing with the conceptual population, then there's no way that we can perform census on the population. So we have to be satisfied with just getting estimates of the population parameters. Okay, so and one way to do that is by calculating what is called a confidence interval. This is a range of values of random variable which we believe at a certain probability, okay, to contain the true value of population parameters. Ya, jadi ini bahasa Indonesia selang keyakinan ya. Selang keyakinan ini adalah suatu rentang nilai, ya, suatu rentang nilai bilangan acak yang kita percaya pada suatu tingkat probabilitas tertentu bahwa dia mengandung nilai sejati parameter populasi yang kita tidak pernah tahu, ya. Kita tidak pernah tahu berapa nilai eksak dari parameter populasi tersebut. Kita hanya bisa mengira-ngira saja. Oke. Okay. CI is always calculated at a prescribed confidence level or significant level. Jadi, pada saat kita menghitung selang keyakinan, kita harus menetapkan dulu berapa tingkat keyakinan atau tingkat keberartian yang kita pilih. Oke. Okay. More on that later. Yeah. So when we report the value of population parameter using CI, okay, confidence intervals, it means that we have expressed that parameter along with its uncertainty. Jadi kalau kita laporkan ya nilai parameter populasi ini sebagai selang keyakinan, artinya itu sama saja kita sudah memberikan juga berapa ketidakpastiannya. Ya. Rata-rata populasi ini adalah sekian dengan batas bawah dugaan berapa, batas atas dugaan berapa. Okay. And this is a side concept here, so you guys have to be aware about the difference between accuracy and precision. Okay. So accuracy means closeness to the true value of the population parameter, and precision means the consistency of repeated measurements to each other. Ya. Ini perbedaan antara akurasi dan presisi. Ya. Akurasi itu kedekatan dengan nilai sejati dari parameter populasi, sementara presisi adalah konsistensi, ya, konsistensi antara pengukuran-pengukuran yang dilakukan secara berulang. Ya. Okay. Alright. Now let's talk about a little bit about confidence levels and definition of confidence intervals. Okay, so all parameter of interest of a population could be calculated from its confidence interval. Jadi maksudnya semua besaran penciri populasi itu bisa dihitung selang keyakinannya. Ya, apakah kita bicara rata-rata populasi, simpangan baku populasi, varians populasi, kurtosis populasi, semua yang sudah kalian lihat di bab 2. Ya, everything that you guys have learned in chapter 2, in module 2, you can calculate the value of their confidence intervals. Okay, and as I told you a few minutes ago, when we calculate CI, we have to specify, okay, what confidence level that we will use. So we typically use these three values, one of these three values, 90, 95, or 99%. So we never ever work with 100% confidence level. That will give you a trivial result. Trivial result means something that is mathematically not wrong, but it doesn't have any practical use. Okay, yeah. So we always work with either 90 or 95 or 99% confidence levels. Okay, all right. Now, can anybody guess? This is just a fun part. Okay, this is just a fun question. Okay, so can anybody guess why these numbers are popular? There's really no there's really no physical law, tidak ada hukum fisiknya that dictates us to use either 90 or 95 or 99%. This is purely an academic consensus. Ya. Jadi penggunaan tiga angka ini murni betul-betul merupakan kesepakatan konsensus. Nggak ada hukum fisiknya mengatakan harus pakai angka-angka ini. Tapi kenapa? Can anybody guess why we like these numbers? Why 90? Why 95? Well, 99 is probably quite obvious. As I told you a few minutes ago, we cannot work with 100% confidence level. So the next best thing is 99%, right? Okay, so how about 90 and 95? Why do we like these numbers? Okay, ask yourself. If you, when you graduate from ITB, right? A few years down the road after you graduated from ITB, and you guys hold a reunion. Okay, so even though your curriculum is clearly a 4-year college, okay, when you do your reunion, you do that by the multiplications of 5 or 10, right? 5 years from graduation or 5 years from commencement to ITB, 10 years, 15 years, 20 years, 25. Why not do 23 years? Okay, why not do 21 years or 11 years? Why the numbers at the end of the reunion have to be either 0 or 5? Can anybody guess? This has nothing to do with statistics, by the way. This is just to keep you guys awake, okay?
I think like to make us feel good, sir.
What?
Make us feel good. It's like, wow, it's 95. You know, it looks good.
Yeah, but somehow it is built on our brain that it looks good, whereas other numbers doesn't look good or hard to remember, right? So, okay, let me ask you this. When you were a little kid, how do you first perform mathematical calculation? Using what? The very, very first time in your life you perform mathematical calculation, what instrument did you use?
Our answer.
Yeah, use your fingers to calculate, right? And most people on Earth have 5 fingers on each hand. So because most of us have 2 hands, then we have 2 times 5, right? This is exactly why we like to work with multiplications of 5 and 10, because this is how we calculate stuff when we were kids. Okay, so it's already programmed in our brain, in our subconscious. Okay, all right. Okay, so what these numbers tells us, this is really this reflects. Oops. These numbers, the confidence levels, reflects the probability of including true values of population parameters in our confidence intervals. Ya, jadi angka-angka ini menyatakan peluang, ya, peluang berapa peluang untuk menemukan atau mengidentifikasi nilai sejati parameter populasi di dalam selang keyakinan kita. Okay. So confidence level is 100% minus significant levels and the other way around. Okay. Jadi ada dua cara untuk menyatakan tingkat keyakinan, apakah menggunakan tingkat keyakinan atau menggunakan tingkat keberartian, significance level. So when we say confidence level of 90%, this is the same as saying that we're using 10% significance level. Yeah. Or when people use significance level, it is customary to use fraction numbers, not percentages. So 90% confidence level is the same as 0.1 significance level. Yeah. 95% confidence level is the same as 0.05 significance level. Okay. Okay, so let's look at this visual example on the right hand side. Okay, so we have here a population with any shape of distribution. Okay, and then from that population we take a large number of samples. Let's say that we take 100 samples. Again, please distinguish between number of samples and sample size. So the green ones, these are samples. So these are individual samples. Okay, these are green bubbles, and each samples consist of a certain number of sample members. Okay, right? So we have, let's say that we have 100 samples, each consisting of n members. Ya, jadi ada 100 sampel yang diambil dari satu populasi, di mana setiap sampel anggotanya adalah n. Ya. And from each samples, we take their sample means. So x bar 1 is the mean of sample number 1, x bar 2 is the mean of sample number 2, and so on. Okay, until x bar 100. Okay. Now, as I will show you later on in the next few minutes, from each sample mean, okay, you can calculate the CI. Okay, you can calculate the confidence interval of mu. Okay, so let me highlight it here. Again, this one here, this is not sample average, but this is population average. Okay. So this is a population mean. Okay. So let me give you one example. Okay. Hold on a second. I need to move to the next page. Okay. So this is how an example of how to calculate confidence interval of mu. Okay. Confidence interval of mu based on x bar. So what we do here is we calculate population. Oops, where is my? Oh, there we go. It's down there. So what we do is we calculate population mean. Please forgive my handwriting, okay? So what we do here again is we calculate population mean based on sample mean, right? Okay. And this formula again tells you that for each value of sample mean, we can calculate a one individual value of mu estimate. Ya, jadi ini adalah rumus untuk menghitung selang keyakinan mu. Kita tidak pernah menghitung selang keyakinan penciri sampel, karena penciri sampel itu diketahui secara eksak. So we never ever calculate confidence interval of sample mean, because the sample mean is known exactly from our measurements. What we don't know is the mu. Yeah? What we don't know is the population mean. So we estimate the population mean based on sample mean. Now, from formula 4-35, you guys can clearly see that from one sample mean, we can calculate one mu, right? We can calculate one confidence interval of mu, right? So if we have 100 samples, then we can calculate 100 estimates of mu. We can calculate 100 confidence intervals. Yeah. Right? This is what is shown here. So from each sample, we calculate one confidence interval of mu. This one here, this there, and so on. So we will end up with 100 confidence intervals of mu. Now, when we say, sorry, I will erase this. There we go. Gets too crowded. Okay. So when we say mean confidence interval at, sorry, this is bad wording, sorry about that. Let me fix it now so we can get it out of the way. Where is my cursor? There. Oh, anyway. Okay, so this one is incorrect. This should be oh, new. Oh, come on. This is not. Okay. There we go. Meet, geez, not that. Now it's correct. Okay, so when we say confidence interval of population mean at confidence level 95%, what does that mean? So now, again, imagine in your mind's eye that you're calculating 100 confidence intervals of the mu. Okay, so you have a large number of confidence intervals, right? In this case, you have 100 confidence intervals of mu. So from these 100 confidence intervals, when we calculate the interval at a confidence level of 95%, then 95% of those CIs will actually contain the value of mu and 5% will miss it. Oke, ya. Jadi saya jelaskan dalam bahasa Indonesia ya. Katakanlah dari populasi ini kita mengambil 100 sampel. Ya, kemudian setiap sampel kita gunakan untuk menghitung selang keyakinan mu. Ya. Maka kita akan mendapatkan 100 buah mu. 100 buah selang keyakinan mu. Ya kan? Nah, kalau perhitungan selang keyakinan tadi dilakukan pada tingkat keyakinan 95%, maknanya adalah dari 100 selang keyakinan, 95-nya kemungkinan akan betul berisi mu. Yang 5-nya tidak akan berisi mu. Kemungkinan tidak akan berisi mu. Ingat, kita tidak pernah tahu berapa nilai eksak mu. Kita hanya melakukan estimasi saja. Okay, so that's the definition of 95% confidence interval. Okay. Okay. All right, so how do we perform the calculations? Yeah. The first case is confidence interval for population mean with known sigma. Now, sigma is, of course, the population. This is the population standard deviation. Okay. There you go. Yeah, I've added that definition here. Okay. So it is assumed that the population standard deviation sigma is known. Please underline the word assume, because again, in most cases, it is not possible to know exactly the value of sigma. Ya, jadi nilai sigma adalah simpangan baku populasi, bukan simpangan baku yang dihitung dari sampel Anda. Okay. So if the sample size is large meaning n is larger than 30, or if we can assume that the sigma is known, then we can use this formula to calculate confidence interval of mu. Yeah. By using what is known as a z variable. Ya. Jadi kita menggunakan suatu besaran yang namanya variabel z, variabel acak z, untuk menghitung selang keyakinan rata-rata populasi berdasarkan rata-rata cuplikan. Besaran z boleh digunakan jika ukuran sampelnya besar, ya. Besar itu artinya n-nya lebih besar dari 30, ya. Atau jika simpangan baku populasinya dianggap diketahui. Assume to be known. Okay. The value of z, the value of variable z, depends on the value of alpha that we select. Ya. Jadi nilai z ini bergantung pada nilai alpha. Alpha itu adalah simbol untuk significance level atau tingkat keberartian. Nilainya ada di sebelah kanan. Okay. So this is the value of z at the three most commonly used confidence levels: 90%, 99, 95, and 99% confidence level. Okay, so when we select an alpha, so this so the alpha, this is the same as saying that alpha is 0.1, right? This is alpha equals 0.05, and this one alpha is 0.01. Okay, so when we select alpha of 10%, then the z value is 1.645. For alpha 0.05, the z is 1.96. And when alpha is 0.01, the z is 2.575. Okay. A little bit of a fun part of your study here. Now, of course, we're not teaching you guys to memorize a lot of stuff, right? But as engineers, there are numbers that will make your life easier if you memorize those. Yeah. For example, the universal gas constant, okay, 0.082 atmosphere liter per mole, or 8.314 joule per mole Kelvin, and so on. Okay. So it will make your life easier if you memorize some of those important numbers. And this is actually one of them. Okay, especially the first two. Okay, the value of z at alpha 10% and alpha 5%. So it is worth to remember these numbers. Okay, for the reasons which hopefully will be obvious within the next couple of weeks. Okay, ya. Jadi memang kita tidak mengajarkan kalian untuk menghafal banyak-banyak hal, tapi kita sebagai engineer itu pekerjaan kita akan jauh lebih cepat kalau kita menghafal beberapa angka, ya. Tetapan gas universal, satuan konversi satuan yang sering dipakai, misalkan 1 feet itu berapa senti sih, ya. Kemudian 1 mikron itu 10 pangkat minus berapa sih, begitu ya. Nah, termasuk ini nilai z ini, nilai z untuk alfa 10% dan 5%. Ini angka-angka yang sering sekali dipakai, makanya nggak ada salahnya dihafalkan. Okay. Okay, so this is the formula for confidence interval of mu. Again, yeah. Let me re-emphasize that we never ever calculate confidence intervals for sample statistics. We only do that for population parameters. Okay. And this is the formula. So this is called the left-hand side. Okay, this is called a lower bound. Lower bound of the CI. And since that is the lower bound, then of course this number is the upper bound. Okay. Okay, and of course this is the sample mean, right? And the term next to the sample mean is called sampling error. Okay, the sampling error is z. Okay, z alpha over 2, z times sigma divided by square root of n. Okay, right? Now, you have learned about how to read Z table in last week's course with Puini, okay? So again, if you want to, but anyway, so I'm a little bit rambling here. So what I want to show you is what is the definition of alpha over 2 there? There's a subscript alpha over 2. So this means that we divide the alpha into two sections, left and right. Now follow my pen, okay? So this is the Z distribution, right? And it's Gaussian like that, okay? Right? This is Z equals 0. Let's find the yellow one. There you go. This is easier on the eye. Okay, so this is Z equals 0, and of course, so that there the Z goes to plus infinity, and there Z goes to minus infinity. Okay, and this is the PDF, the probability density function of Z. Okay, so and where's alpha? Where does the alpha comes into play here? So when we say, let's say that, for example, we define alpha as 0.05, okay? So let's say that you're working with alpha of 5%. So the 5% alpha is divided into two tails. Dibagi menjadi dua ekor. Ya. The left-hand side tail and the right-hand side tail. Okay. So the area that the hatched area, jadi area yang diarsir ini ya. Remember the definition of probability density function. The area under the curve is a probability number. Okay. So what happened with this 0.05? It is divided into two equally sized probability values. So on the left-hand side here, the area is alpha divided by 2, half of alpha, which is 0.025. Okay, and likewise, the area here is also 0.025. Okay, so it's alpha divided by 2. The reason why we need two areas is because we have to calculate the lower bound and the upper bound of the CI. Okay. All right. Now, any questions so far? It is quite obvious from the formula that we have here. Okay. Oops. There you go. That's my, okay. So it's quite obvious from these numbers that if we increase the value of alpha, then we will increase this area here, right? So for example, you guys want to use also, if you want to use alpha of, let's say, let me write it down with a different color, okay? So let's say we want to work with alpha 0.1. Okay. This doesn't sound right, actually. Yeah, okay, yeah, that's right. Okay, so let's say that we want to work with alpha of 10%. So it means that the area will be, each will be 5%, right? Each will be 5%. So in order for the area to be increased, then the limit, okay, the limit of the integration has to move inwards. It has to move inwards, right? So now the limit is here. Okay, and the area, okay, So from minus infinity to this limit here, this area is, so the total, okay, this entire area is 0 0.05. Likewise, this area here is also 0.05. So the total becomes 0.1. Okay. And the value of z, for this case, for the green case, the value of z, this is 1.645. And the yellow one, sorry, this one is minus 1.645. Yeah. And the yellow one then is plus minus 1.96. Okay. All right. Everybody clear for that? On that, I hope. Now let's move on to the next case. Okay. So, which is the confidence interval for population mean with unknown sigma. Now, this is a more, as you can probably imagine, this is a more general case. This is the more realistic case. Okay. So, in most situations, we don't know the value of sigma. Yeah, we don't know exactly the exact value of sigma. So there's no way to use z variable, especially if the sample is small. Okay, so if sigma is unknown, yeah. Okay, so if the sigma is unknown and the sample size is small, okay, the sample size is small meaning n is less than 30. So we can use random variable t instead of z. Okay. Instead of z. Okay. The formula is analogous to the previous case. Okay, so this is still the sample mean, but now the z is replaced with t. Okay, and the sigma is replaced by s. S is the sample standard deviation. Sample SD means that you have to calculate S from your sample. So it cannot be assumed to be known. It has to be calculated from your sample. That is the reason it's called sample standard deviation. Okay. Now the t value is determined by alpha and degree of freedom, which in this case, the degree of freedom is equal sample size minus 1. Yeah. Okay. All right. Any questions here for now? If not, I will move on to the next page, which will tell you how to read the t table. Okay. All right. Okay. Let's move on to the next one. This is this is the t table. Yeah. Hold on a second. Oops. You bounced right off there. There we go. That's nice. Okay. Um, there you go. And the first column, okay, the first column gives you the degree of freedom. Now remember the symbol here. This Greek letter is called nu. Yeah. This is a Greek letter which is pronounced as nu. Okay. And alpha, this is the value of the probability. Okay. Okay. So alpha is located on the top row. Okay. Now pay attention to this graph here. Okay. So this tells you that the way this table is laid out is the probability is calculated as a right-hand side, right-tailed probability. Okay, this is, we call this a right tail probability. Okay. Okay. And now what these numbers are, these numbers, okay, so the numbers inside here, all of these numbers, okay, these numbers are the t value, this one here. Okay. This is different from Z table. In Z table, the number inside the body of the table is the probability, is the alpha. Okay. Here, the alpha is read as the row. Okay. So this table, of course, only gives you a select number of alpha. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values of alphas. And if you need an alpha value that is not contained here, then you always, of course, you need to do an interpolation. Okay, ya. Jadi saya ulang dalam bahasa Indonesia ya. Ini dinamakan dengan tabel T, distribusi T. Oke, berbeda dengan kalian bisa lihat bahwa anatominya berbeda dengan tabel Z. Ya, di sini di kolom pertama adalah derajat kebebasan, diberi simbol huruf Yunani new. Ya. 1, 2, 3, 4, dan seterusnya. Ini tabelnya saya potong, jadi derajat kebebasannya masih bisa lebih banyak lagi kalau kalian lihat di buku teks. Kemudian nilai alfanya itu diberikan di baris paling atas. Jadi di sini tidak semua nilai alfa diberikan. Di sini nilai alfanya ada 0,4, 0,25, dan seterusnya gitu ya. Sehingga kalau kalian memerlukan data yang nilai alfanya nggak sama dengan ini, ya terpaksa kita melakukan interpolasi. Lantas angka-angka yang ada di dalam badan tabel ini apa? Nah, ini adalah nilai T-nya. Ya, jadi beda dengan tabel Z. Kalau tabel Z, angka yang ada di dalam badan tabel itu adalah nilai probabilitas. Ya. Di sini ini bukan probabilitas, tetapi nilai T. Ya, batas integralnya nih. Oke. Kemudian kalau kalian perhatikan gambarnya, ya ini penting sekali untuk memahami apa maksud gambar ini. Ya. Artinya, probabilitas alfa ini dihitung sebagai integral satu sisi sebelah kanan. Atau istilah bahasa Inggrisnya adalah right tail probability. Oke. Nah, kita lihat satu contoh sekarang. Oke. Alright, so the example is, what is the t value, okay, when alpha is 5% and n equals 10? Ya, berapa nilai t pada saat alfanya itu 5% dan ukuran sampelnya 10? Ukuran sampel 10, bukan derajat kebebasan 10. Oke. Nah, alright. So because we need to calculate the lower and upper bounds, yeah. So the value of alpha have to be divided into two sections, into two equally sized probabilities, meaning that we have to work with alpha divided by 2, which is 0.025, this one here. Okay, so we read off vertically from the column at which alpha is 0.025. Okay. And we found, and we need to find the t value that corresponds to the correct degree of freedom. Yeah, and we know from the previous formula that the degree of freedom is n minus 1 equals 9, right? So the t value is this one. Okay, so this is this is the degree of freedom, and this is alpha over 2. And this is the t value that corresponds to those two numbers, which is 2.262. Yeah. Okay, any questions? The shape of the t distribution is actually quite similar to the Gaussian distribution or normal distribution, actually. And in fact, if the degree of freedom approaches infinity, then the asymptotic case for the T distribution will become Z distribution. Ya. Nah, jadi bentuk dari distribusi T itu mirip dengan distribusi Z. Semakin rendah derajat kebebasannya, maka distribusinya semakin lebar. Ya, ini menunjukkan ketidakpastian yang lebih besar. Nah, jika derajat kebebasannya mendekati tidak terhingga, maka secara asimptotik distribusi T akan menjadi distribusi Z. Okay. Now the reason why I'm putting the picture of Guinness beer here is because the person who discovered the T distribution worked in the Guinness beer factory, okay, in the Irish Republic several decades ago. So he has long passed since. Okay. Okay. So these two persons, Abraham de Moivre and Carl Gauss, these guys invented the Z distribution, okay, the normal distribution. We typically say normal distribution as Gaussian distribution, but actually the original inventor of that distribution is not Gauss, but de Moivre. Okay. Unfortunately, the way de Moivre write down the math is too difficult for people to understand its practical implications. So the more practical version of the Z distribution was invented by Carl Gauss. That's why we frequently refer to it as Gaussian distribution. Okay. And William Gosset is the one who discovered T distribution, which is very, very useful in the world of statistics because it enables us to draw conclusions based on small sample. We call those small sample statistics. Okay. Yeah. You can imagine how expensive it will be if everything has to be measured with a sample size of over 30. Okay. If everything has to be done using big samples, then things will get much more expensive. Okay. So William Gosset worked in this Guinness beer factory in Ireland when he invented this T distribution. Okay. All right. Any questions here? If not, let's do a 5-minute break, and I will give you a calculation example after this. Okay. So let's do a 5-minute break. Let's take 5. Okay. Okay. All right. So this is an example that's available in our textbook. Okay. And this talks about a measurement of mechanical property of material. So now you don't have to think too hard about it, but for now, uh, just keep it as your knowledge that there are several ways that we can by which we measure the mechanical strength of materials. Ya, jadi contoh 8.1 ini adalah salah satu dari sekian banyak metode pengukuran kekuatan mekanik dari bahan. Ya, namanya Sharpie test atau Sharpie impact test. Okay. Sharpie V-notch test. Ya, intinya sih gini ya. Intinya misalkan, oke, ini materialnya misalnya ya. Kemudian material ini dipukul dengan suatu alat tertentu, alat standar. Okay, so this material is being hit by a standard instrument at a standard force. Okay, and then what is being measured is the impact energy in the unit of joule on the specimens. Okay, it's based on the measurement of impact point. Okay, jadi yang diukur adalah bekas benturan yang terjadi pada benda tersebut, ya, dan diperkirakan berapa energi impact yang terkena pada spesimen tersebut. Okay, so this researcher performed. Let's calculate how many measurements that he or she has performed. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this measurement was repeated 10 times. Ya. Jadi pengukurannya diulangi sejumlah 10 kali. Hasilnya adalah ini. So these numbers are the result of the Sharpie V-notch measurements. Okay. Next, we assume that the impact energy is normally distributed with sigma equals to 1 joule. Jadi dianggap energi impact ini terdistribusi secara normal, artinya mengikuti distribusi Z atau T. Ya. Dengan sigma, simpangan baku populasinya dianggap diketahui sebesar 1 joule. Ya. We want to find the 95% confidence interval for mu, okay, the mean impact energy. Okay, so the required quantities are the Z values itself, because we're using alpha of 5%, then alpha divided by 2 is 0.025. So the Z value is plus minus 1.96. Okay, remember we have lower bound and upper bound. Okay, N is equals to 10, so the sigma is assumed to be known at 1 joule. Okay, and if we calculate the average of these 10 numbers, we will obtain 64.46. So the confidence interval, the 95%, this refers to the confidence level. Okay, so distinguish between confidence level and confidence interval. This is the confidence interval, okay, and 100 minus alpha is the confidence level. Okay, oh, you know what? I'm gonna copy and paste this to our PowerPoint to facilitate our calculation. Hang on a second. Copy image. Okay. Yep, here. So new slide. That only sample. Oops. There we go. Oops, not that one. Yep, this one. Okay. Oops. Yep. Okay. Yeah. Okay, so this formula is for confidence interval. Right? And alpha, okay, 100% minus alpha is confidence level. So please keep in mind the difference between these two terms. Okay, there's confidence interval and confidence level. Yep. And there's the calculation. Yep. And this is the result. So this would be the lower bound, and that's the upper bound of the population mean. Okay, so now you can observe that instead of reporting the mean as simply 64.46, now we're reporting it as this range here, this interval. So the lower bound is 63.84 and the upper bound is 65.08. Okay, right? Or you can also, of course, you can also state it like this. Okay, so, this is the sample means. This is not population mean, right? Sample means plus minus sampling error, which in this case is 1.96, right? Times 1. So the sigma is assumed to be 1 divided by square root of 10. Okay. Same thing. You can express it as lower bound and upper bound like this. Okay. Or you can express it like this. So, okay. Yep. Any questions here? So this is what we do if we assume that sigma is known. Now, what if, okay, what if this assumption is, where is my pen? There we go, that's my pen. This presentation window is messing things up a little bit. There you go. Yep. So what if this assumption is not valid? If sigma is unknown. Okay. So in this case, we cannot use z distribution. We have to use t distribution because the sample size is small. Okay, n is only equal to 10, right? So mu then becomes sample average, right? Plus minus t, okay, calculated at half of alpha and at a specific degree of freedom, okay, times s, because we don't know what the value of sigma, so sigma has to be approximated by s divided by, like that, okay. Again, this formula is used if sigma is unknown. So we have to calculate sigma from the sample, okay. All right. Now, I'm going to give you guys a few minutes to work on this sample, okay. We have learned a few minutes ago about how to read the t table, yeah. So I give you guys until, so this is what, 10 minutes, okay? I will give you guys 12 minutes. So we'll meet again at 9. Again, for those of you who cannot extend your attendance after 9 a.m., that's fine. You can move on to the next class. But for those of you who do not have any class, please stick around for the next 20 to 30 minutes. Okay. I do apologize that for the extended course, but we need to do this because next week it will be exam week, and this is included in the exam. Okay, so I need to extend the class by 30 minutes. Yeah. Try to do this calculation, the one here. Okay. Where's my pen? Yeah. Try to do this calculation manually. You can use the T table. The T table is already uploaded in EduNext, or certainly you can read it. You can use the one in that is available in your textbook as well. Yeah. So this would be the X bar is of course still 64.46, right? Then plus minus, you have to look up the value of the T, and then you have to calculate the S, okay? Sample standard deviation divided by square root of 10. So calculate these two numbers and then finish this calculation to determine the confidence interval of mu for the case of small sample. Okay, go ahead. I will give you 10 minutes. Okay, we will reconvene at 9. And of course, you guys can take a screen capture of this, okay? Because I will exit the. Oh well, wait. Let me exit the presentation. However, I'm going to keep the ink annotations. There we go. Yep. You have any questions? If you guys have any questions, please feel free to ask us now. Okay. In fact, we have already done the lookup of this of the t value from the previous example. So all we have to do now is just to calculate uh, the standard deviation of the sample and then the rest of the calculation for the sampling error. Now, have anybody done that? Maybe Puwini can point to one of the students.
Yeah, okay. Who want to raise hand voluntary? Azra?
Sorry, ma'am, I haven't finished. I don't.
Okay.
Yeah.
Or maybe just look at your work and then we can discuss. Yeah. That's fine because I know it may be difficult for most students. I think Pak Miki, because usually in the class we do it on the whiteboard, yeah, and then
Whiteboard.
by steps, and then we can pause and each student can ask, or we can take a look around and then check one by one. But now a little bit difficult, especially if you didn't raise hand or didn't ask, yeah. So we don't know which one of you who understand or which one is not. So I think if you can, maybe let's start with Azra. Can you show your work or what have you done so far? That's fine.
Oh, wait. I haven't scanned it though, ma'am. Wait, give me a minute.
What? Could you repeat that, please?
I haven't
You haven't done-
scanned work, sir. Just give me a minute, sir. Thank you.
Okay.
Oh, you do it in your in the paper, yeah. Okay.
Or I can make it easier. Can you read off your sample standard deviation? Just read the value to me.
Well, for me, I just found out the confidence level and precision of estimation that the length of the 95% confidence interval is 9.92.
You're doing that with Excel, did you?
Yeah.
No, no, no. I want, oh, okay. I want you
Mhm.
guys to be able to do this manually first before we go to Excel. Okay. So you guys need to be, you need to get up on your feet and do this manually first. Okay. And then we will show you how to do it with Excel, right? Because we want you guys to know what's going on in Excel. Yeah. Just because you have the tool ready at your disposal doesn't mean that you have to rely on that tool, 100% of the time. Okay, we want you guys to understand what's going on here, and also this is also true for the exam. Okay, so when you ask you guys to calculate manually, you guys cannot use Excel. Okay, you have to be capable of doing it manually and with Excel, right? So you cannot just say because I've seen some of these pattern in students, okay, where it doesn't matter if we ask them to perform calculation manual or with Excel, they just copy paste whatever calculation that's being done in Excel in their exam problem, and that is not acceptable. Okay, so when we tell you to do this manually, well, do it manually. Okay, when we tell you to do this using Excel, then you can use Excel. Okay, so all you have to do is actually calculate the sample standard deviation and look up the value of the t, which actually we have done it here anyway, right? So we have done the lookup value of the t here actually. So it so happens that the n is also equals to 0 and alpha is also equal to 5, that's 5%. So the t value is already been determined here as 2.262. Okay, so here, and if you're handy with Excel, note that I'm not asking you to calculate the sample standard deviation manually, you can calculate this quite quickly. Yeah, so you can calculate the sigma, the S using Excel, but we ask you to calculate this term manually. Okay, go ahead. So what is the sample standard deviation? You know, if you use this, if you calculate this one in Excel, before I'm done talking, you guys should have been done with this in Excel, right? Just to calculate the standard deviation of 10 numbers, 64.1, 64.7, and so on. Okay.
To be honest,
Can anybody? Yeah. Go ahead, Aurel. Okay, Aurel.
Yes, sir. So
Yeah.
I tried to calculate it using like a calculator for the standard deviation. So I'm not really confident with my answer, but my answer is 0.215, but I'm not sure.
What is the number again?
0.215, sir.
0.215. Okay, let's try that.
Pamiki, you haven't shared your screen.
Oh, yeah. I think it went off by accident. There we go. Okay, so this would be 64.46 plus minus the t value. Again, this already been determined from the previous slide. Okay, is that right? Is that correct? 0. Yep. 2260. Okay, and multiplied by 0. What is the standard deviation again, Aurel? Is it 2.15 or something?
2.215, sir.
Okay, like that. Okay, so what is the sampling error? Can you calculate this term as well?
It's 0.154, sir.
That's all right. I believe you. I haven't done it myself, but it seems to be correct. Anyway, okay. So this is the confidence level of mu. Okay, if the sample is small and we cannot assume that the sigma is available. Okay, now let's compare this to this one. Okay, so this would be, so the lower bound will be oh geez, okay, okay, could you also calculate, could you calculate 64.46 minus this sampling error? So this would be 64 point what?
306, sir. 306.
306. Okay, I'm gonna write it off to just 2 decimals, so like that. And the upper bound is
Is 64.661.
okay. All right, okay. Yeah, it seems to be a rather narrow, but anyway, so, oh, I get it. This is because the S, the value of S, this one here, the S is much smaller than this one here. Doesn't matter. It doesn't matter. Okay. Anyway, so that is that's how you calculate the confidence interval of population mean when we assume that the sigma is known or unknown. Okay. So if this sigma, if this S, okay, if this is assumed to be sigma, then of course the T will be replaced by Z, and the Z will be 1.96, right? So jadi seandainya 0,215 ini dianggap sigma, bukan S, ya, artinya ini dianggap sebagai simpangan baku populasi, maka T-nya boleh diganti dengan Z. Kita semua tahu pada alfa 5%, nilai Z itu adalah plus minus 1,96. Okay. So when we do that, we will end up with a narrower confidence interval, right? And that is the reflection of the difference between Z distribution and T distribution. Okay, T distribution for the same alpha, okay, for the same alpha, T is always wider than Z. It reflects a greater degree of uncertainty. Okay. All right, now let's move on to the last segment of this week. Okay. Okay, wait, I have to exit. There we go. So last one is this one here. 4.3. There we go. Okay, now as I've told you before, we can perform this calculation. We can calculate the standard deviation, the confidence interval for any descriptor. So what we did just now is just one of several descriptors that is available. So we calculated, we discussed about how to calculate the sampling, the confidence interval for population mean. Here, we want to calculate the confidence interval of sample, of population variance. Okay. All right. Now, to do that, what we need is this distribution called chi-square. Okay. Wait. There you go. That's what I'm looking for. Okay. So the distribution that we need. So remember that for the distribution that we need for CI of means. Okay, we use either C or T, right? So for confidence interval of variance, we use this quantity called chi-square. This is the Greek letter chi-square. Okay, and this is the shape of the chi-square distribution. Okay, as you can see, it is not symmetrical, right? It's not. It's asymmetrical. And it also depends on on the degree of freedom. Okay. So the value of chi-square depends on significance level and degree of freedom. Again, in this case, the degree of freedom is calculated as n minus 1. Now, everybody follow me so far? Okay. So we have been introduced with three. Three probability distributions, three random variables that we use for confidence interval calculation. We know the variable Z and T, and now we know the variable chi-square. Okay, all of these three variables are random variables for different purposes. Okay. So again, Z and T, you use those to calculate the confidence interval for population mean. Z is used if the sample is large, or if the sigma is known, okay, if the population standard deviation is known, and you use t when the sample size is small and sigma is unknown. And you use chi-square when you want to calculate the confidence interval of variance. And you simply use this formula here. Now, in exams, we generally do not require you to memorize formulae, because some of the formula in statistics can be quite long. So, but you have to know which one to use in what situation. Okay, so if the problem asks you to calculate confidence interval of sample of population mean, then you need to use either Z or T, and you need to use the formula that we discussed a few minutes ago, right? If the problem asks you to calculate the CI of variance or population variance, then you use equation 4.62. Okay, remember, any population descriptor, whether it's mean or average or variance, standard deviation, you can calculate the confidence interval of those numbers. And the reason why we need to calculate the CIs is because those numbers are from sample, right? Those numbers are from sample, but we need to draw conclusion of population based on limited data from sample. Okay, so from you see, as you have seen a few minutes ago, what you learned was how to estimate mu, right? Mu is population mean based on X bar. X bar is sample mean. Okay. Here, you learn how to calculate sigma based on S. Okay. So this one, okay, this is population variance. Population variance. And this one is sample variance. Right? So again, this is application of central limit theorem. There's a correlation between sample statistics and population parameter. In this case, this is a correlation between population variance and sample variance. Okay. So the value of now the one thing that you have to be careful about chi-square is because it is not symmetrical. Okay, as you can clearly see, the shape is not symmetrical, so you cannot state, you cannot express the population variance as being like this. You cannot do this. Plus minus sampling error. Okay, so this doesn't work. Okay, because the shape of the chi-square distribution is not symmetrical. So you have to determine from the tables separately this one and that one. Okay. All right. Here we go. Yeah. So this is called a chi-square table. Yeah. The layout is quite similar to T distribution. Yeah. Okay. In the sense that the first column, yeah, the first column is degree of freedom, and the first row is the probability, is the alpha. And here in my example, the probability is given, the alpha is given as a right tail distribution. Okay, so this is alpha, not alpha over 2, but just alpha. Yeah. And again, because in a confidence interval problem, you need to find a lower bound and an upper bound, then you need to find two values of chi-square. Okay, chi-square that is associated with the lower bound, and that one associated with upper bound. Okay, so in general, again, let me repeat, in general, confidence interval calculation requires two boundaries, lower bound and upper bound. That means you need to find two values of chi-square. Yeah, if you're working with, there you go. Let's see. Let's discuss this based on example. Okay, so the data is data of weight per chocolate candy, per piece of chocolate candy in one package. Okay, and we are asked to calculate the confidence interval of the population variance at 95% confidence level. Okay, so what we're doing here is we take one package of chocolate candy and assume that this one package represents the entire population, right? Okay, so we open the package and we weigh the chocolate candy piece by piece in that one package, and we come up with this data. So let's assume that we get the N is 30, okay? The sample mean is 1.25 gram, okay? So this would be the weight of one piece of candy, not the entire bag, okay? Just one candy. So 30 means we have 30 pieces of individual candies, okay? And the standard deviation of the sample is 0.262 gram, okay? All right. So we need to calculate the confidence interval of sigma, yeah, using this formula. Yeah. Okay, now let's work this out. So we set alpha to be 5% because we're using a 95% confidence level. Okay, so the alpha is 100% minus 95, right? The degree of freedom is, in this case, n minus 1. N is 30, so n minus 1 is 29. Now let's find the critical value of, or the limit values of chi-squares from the table. Remember, we need to find two values, okay? And because this is the way our chi-square table is laid out, so the first search on the left hand on the right hand side, this would be alpha over 2. Okay, right? And since our alpha is 0.05, so this one is 0.025. At degree of freedom equals to 29. Okay. So by looking at the table, we found that value to be this one here. Okay, 45.7. So this would be the chi-squares which is located on the right-hand side of the distribution. Now we have to find the other one on the left-hand side, right? We have to find the one here. Okay. And the area here, okay, the area is, of course, the same on the right-hand side, 0.025. However, since our table is based on right tail distribution, then we need to find the value of chi-square at which the probability is this one. Again, let me repeat. So we need to find the value of chi-square for which the value of probability is actually 1 minus 0.025. Again, this is necessary because the table is based on right-hand side integration. Ya, karena tabel ini didasarkan pada integral sisi kanan, probabilitas sisi kanan. Ya, bukan dua sisi, bukan satu sisi sebelah sisi, tetapi satu sisi sebelah kanan. Jadi kalau kita ingin mencari nilai chi-square yang menyebabkan, ya, yang menyebabkan integral sebelah kirinya itu 0,025, gitu, maka hasil integral sebelah kanannya adalah 1 minus 0,025, equal to 0.975. So what is the value of this chi-square that produces that value of probability? This one. Yeah. There you go. 16.05, 16.047. Okay, so this is the value of the left-hand side chi-square. Yeah. Now be careful when entering these values to the formula, because in the formula, watch here, okay, note here that in the formula, they become the denominator, not the numerator, but they become the denominator, okay, menjadi penyebut, ya. Karena mereka menjadi penyebut, maka jangan lupa ini harus dibalik, ya. So the big number, this one, this is the big number. The big number goes to the left-hand side of this equation, this one. Yep. So you'll end up with a ratio that is smaller. Conversely, the smaller value of chi-square must go here, the upper bound of the CI. Ya. Jadi kalau kalian salah hitung, ya ini kalau kalian salah masukkan angka, gejalanya jelas. Batas bawah, lower bound from the of the confidence interval gets bigger than the upper bound. It means that you're putting the wrong numbers. Ya, jadi kalau kebalik, kalau batas bawah dari CI-nya itu lebih gede daripada batas atas, artinya kalian salah memasukkan, kalian kebalik memasukkan chi-square-nya. Ya, itu aja. No big deal. All you have to do is just just repeat your calculation with the correct way. Okay. All right. Any questions here? If not, okay, there will be time. I would like to discuss this slide with you, but I think I need to find another time for this. This is a very interesting application of statistics actually for quality assurance. It's something that is quite important for you guys. Okay. Okay. No questions? Okay, if not, I do have a word for you guys. This being only the week number 4. Okay, so next week we will have the exam in week 5. I think I can speak for other faculty members as well, not just me personally, but also for Bu Ini, for Pak Sibi, for everyone, for all the teaching team in our statistics course. This is only week 4, you guys, so you need to have a good stamina for the rest of the semester, okay? And we need you guys to pay attention, okay? So it's really, I fully understand that this is a challenging situation for you guys, also for us actually. So this work from home thing is clearly actually it has been hard for all of us, okay? But actually it also reveals opportunities, okay? So you guys need to understand that things will very unlikely things will go back to how it's been before the pandemic, okay? Meaning I don't think ITB will ever go back to fully offline courses, okay? Most likely what we will end up with after this pandemic is over is probably most likely ITB will keep on giving these online-based courses. At most, we will administer a blended type of learning. Okay, so probably this is in my imagination. Okay, but I think this is quite rational. I think Bu Ini can also chime in on this. So in the future, you don't imagine that all of the classes will be done at school in Kampus Ganesha or Jatinangor, but most likely the courses, the non-lab courses will probably be still done this way, okay? And Of course, laboratory, we hope that the laboratory will be reopened soon, and you guys can go can do your lab practicals in school, okay, for your MPA, your lab tech 1, lab tech 2, penelitian 1, penelitian 2. But classical courses will most likely still be delivered on an online basis. At least a significant portion of the class will still be delivered online. That's what I'm thinking. That's going to happen for the next, I don't know, maybe for the next 5 or 10 years or even forever. Okay, so you guys need to be more active learners. Okay, yes, I know it's more fatiguing. It's more tiring to do online classes like this. But this is the best way so far. Okay, and I think this would be the way of the future as well. So you need to be active, and we really don't appreciate students who just log in and then sleep in front of a computer, okay, or away from keyboard. So because we have put a lot of time and effort to preparing these course materials, so we ask for your active participation. All right. The reason why we don't require you to keep an open cam, to keep your camera on, is because we respect your need to conserve your quota as well. Okay, but if from our interaction it seems that the students are not as active as we want you to be, then we might consider to they require you to keep your camera on all the time. Okay, so please be mature ya. Jadi tolong bersikaplah dewasa. Tadi sebetulnya tugas yang saya berikan itu gampang banget ya. Kalian tinggal buka Excel, tinggal menghitung simpangan baku di Excel. Bahkan pakai kalkulator pun bisa seperti yang dilakukan Ariel tadi. Jadi sebetulnya gampang banget ya. Nah, kami meminta aktivitas kalian yang jauh lebih tinggi ke depannya. Jangan hanya login terus entah kemana gitu ya kalian ya. But we need you guys to pay attention. Don't just rely on recorded sessions ya. Jadi jangan hanya mengandalkan perekaman saja. Nanti gampang lah, nanti bisa dilihat nanti belakangan. Sekarang tinggal dulu, sekarang ngerjain yang lain. No, we don't want that ya. Kami ingin perhatian kalian fokus ya. Ya kalau gini terus nanti kami kasih kuis gitu aja mungkin ya untuk gampangnya gitu ya, biar kalian tetap fokus gitu ya, sekali-sekali kasih kuis gitu ya. Nah, mau gitu atau mau aktif ya. Kalau kalian nggak mau banyak kuis, ya kalian mesti aktif, tanya ya kalau memang atau kalau ditanya ya kalian menjawab gitu ya, jangan diem aja semua. We don't like silent classes, okay? Right? Bu ini barangkali ada mau yang ditambahkan? No? Okay, that's okay. Yeah, jadi so for the next classes we ask for your active participation, right? So when we give you 10 minutes to work, then make it use that time to work. Okay, use that time to work the examples. Don't just wait for us to feed you. Ya, jadi jangan menunggu kami untuk mengumpani kalian. Kalian adalah pembelajar aktif. Kalian nggak akan survive kalau kalian tidak bertindak sebagai pembelajar aktif di situasi WFA ini. Ini akan terus kayak gini loh, ya. Saya ITB itu tidak pernah membayangkan nanti situasi kan kembali seperti zaman dulu, kalian kuliah offline sepenuhnya, enggak loh. Paling banter ITB akan mempraktekkan yang namanya blended learning. So it will be a mix of offline and online courses. Theoretical stuff will most likely still be delivered on an online basis like this. So this is the new age, you guys. Okay, inilah normal yang baru. Kalian nggak bisa lagi hanya mengandalkan oh ya nanti kan yang penting pas mau ujian baca dulu gitu ya, lihat dulu. No, you cannot do that. Kalian mesti menjadi pembelajar yang lebih aktif lagi. Okay? Because the risk is greater if we allow you guys to do the classes all offline. Ya. Jadi untuk beberapa tahun ke depan, seenggaknya itu ITB masih tetap akan begini. Ya. Paling ya kalian kemungkinan ya praktikum ya tentunya diusahakan di kampus. Tapi kuliah-kuliah itu kemungkinan besar masih akan tetap sebagian itu online. Ya. So you guys really need to get used to it. Ya. Alright? Any questions? No? Okay, if not, I will see you next week. So remember, next week is exam. Between now and the exam, we hope that we have enough time for us to prepare our assistants and for them to give you tutorial sessions. Okay. All right, I'll see you guys next week. So remember, next week is exam week. Okay. There will be further instructions on how to do the exam. Yeah. Okay, thank you very much for your attention, and we'll see you next week.
Thank you, sir, for the feedback.
Thank you
Yeah.
very much, sir.
Okay.
Thank you very much, sir. Thank you, sir.
Thank you, sir.
Mhm.